Hello, everybody. My name's Sam. Today, we're going to have a look at some basics of quantum computing, in particular, quantum circuits. I've tried to make this kind of little video as understandable as possible, so we're only going to require a basic understanding of the ideas of linear algebra and vector kind of matrix multiplication and vector sort of stuff. Excellent. We're going to look at the basic idea of what a qubit is. We're going to look at superposition. We're going to look at some simple quantum gates. And then we're going to do a simple implementation to entangle two qubits. I hope this is interesting. Without further ado, let's get on. All right. First off, what is a qubit? Now, a qubit is this kind of thing inside a quantum computer. In normal computers, we have bits, and they can be in kind of two states. They can be on or they can be off. And those two states are kind of definite. The bit is either on or it's off. In a qubit, things are slightly different. It's usually an electron with spin up or spin down or something like that. You have this quantum particle that represents your property, and it has two states, up and down. But the key thing here is that they can be in a superposition of states. So we're going to use this notation here to represent our qubit, A. And A can be in a superposition of states of the states 1 and the state 0. And the idea here is that we'd say that the state of A is equal to some constant A times the state 1 plus some constant B times the state 0. All right? My Microsoft Paint drawing is not very good. I'll have to ask Pirate Software for some tips. But the idea here is that A and B represent the probability amplitude of each specific state. So in this case, the probability amplitude, our probability amplitude is a bit weird, but effectively what it means is that when we square A and we square B, it gives us the probability of that state. So let's think of a basic example here. Let's erase this. If we have a qubit, A, in a state 1 over root 2, state 0 plus state 1, what we have is this 1 over root 2 obviously distributes over this bracket. So we have a half 1 over root 2 state 0 and 1 over root 2 state 1. And when we square this, which is what we've kind of said initially, we get our probability. Remember, this is the probability amplitude. We want to get probability density, or just the probability in this case. And so when we square 1 over root 2, we get 1/2. So therefore, the probability of it being in state 0 is going to be 1/2. And the probability of it being in state 1 is also going to be 1/2. Excellent. So this expression here represents a qubit A in a superposition of states, an equal superposition of states, between 0 and 1. Nice. Perfect. Something that's slightly complicated about this is that kind of our coefficients for kind of A and B don't always have to be real, so they can be imaginary numbers. We're going to keep them relatively real for this demonstration. I will talk about how they can be imaginary numbers in perhaps another video. I feel like it's a little bit out of the scope. But the idea here is that we want to think of squaring A to get the probability of state 0 and squaring B to get the probability of state 1. So, and it is entirely possible for some qubit. So some qubit A to be in a state that is 100% definite. And we'd write it like this, but obviously you can kind of substitute in the coefficients 1 times this plus 0 times our state 1. And this is the idea. They can be in a superposition of states. They can be definite, like a regular bit in a computer, but the the advantageous part of quantum computing is that qubits can be in a superposition of states. That's the main idea. Excellent. Now, one way we can kind of talk about qubits that'll be really helpful for doing kind of operations with gates and stuff like that in the future. Um, we're going to write them as a vector. So if we actually, I'll delete this part and leave this expression here, because this is kind of a good thing to have in the back of your mind. Move this up there and shrink it down a little bit. All right, perfect. So what we're going to do is we're going to imagine writing A as a vector. And it's a bit weird to think of as a vector. I mean, most people would think of a vector as some kind of position in 3D space, or in 2D space for that matter, kind of a direction. What we're going to do is we're just going to think of it as we're going to substitute A and B to get our vector A, B, like this. So we have our values, we take our values straight from this, and we put them into our vector AB. And what each column represents here is we're thinking of these states rather than as kind of abstract ideas of states. We think of these states themselves as unit vectors. So the state 0 is itself a unit vector, and the state 1 is itself a unit vector, and therefore A is the vector representing the superposition of states between 0 and 1. And if we remember, squaring these terms will get us our probability of each state. So since the probability can never be higher, the total probability can never be higher than 1, we can actually understand that in this case, if we take A and B to be real, our possible values of A and B lie on the surface of a circle, or the circumference of a circle in the 2D plane. So this is another way of thinking about it, but it's not necessarily needed. The main idea is we're taking this form and we're putting it into our vector form here. All right. The next thing we're going to talk about is how quantum gates work and how they operate on qubits and how we can represent them using matrices. So firstly, we imagine our qubit A, and we're going to represent it in a circuit diagram as a line. So A is this qubit that moves along. We imagine kind of a time axis in this direction, and this line then gets operated on by certain gates. So, for example, if we put a gate here and a gate here, this shows us that we operate on this gate first, and then we operate on this gate. And our end state we're going to call A prime. Excellent. The first gate we're going to look at, if I get rid of this kind of jargon here, the first gate we're going to look at is called the NOT gate. And it works very similar to how a NOT gate in simple binary computing works. If the qubit is in a definite state of off, then the qubit becomes then the qubit turns into a definite state of on. And if the qubit is in a definite state of on, then the qubit turns to a definite state of off. But a NOT gate in quantum mechanics or in quantum circuitry does more than just a NOT gate in binary circuitry. It doesn't just flip definite states, but it also flips probabilities of or superpositions of states. And the way it does this is it flips A and B, so the values for A and B in our coefficients here. So say A took a value of root 2 over root 3, and B took a value of 1 over root 3, then what would happen, remember that when we square A and B, we get the probabilities. So the probability of finding 0 in this case would be A squared, which is root 2 over root 3 squared, which is 2 over 3. And the probability of finding B would be 1 over 3. So we've kind of got an unequal distribution. what our NOT gate would then do was effectively flip the coefficients of A and B so that the probability of our 0 state is now 1/3 as opposed to 2/3, and our probability of our 1 state is 2/3 as opposed to 1/3. So it's kind of swapped this. Now let's think about what this means in our vector form. So if we take our coefficients, as a vector, a, b, as we discussed how to do earlier, and we're going to multiply it by some matrix M. Actually, we're going to use n because this is a NOT gate, so it makes sense to denote it with an n. So we have some matrix n multiplied by AB, and this gets us BA. This is what we want. How do we determine n? Well, there are many ways of doing it. Those of you with backgrounds in linear algebra would understand how to do this. I'm going to skip over it because it's not really within the scope of the video. The idea is that n is going to be equal to 0, 1, 1, 0. So we've now represented our operation here, our quantum gate, as a matrix. And so whenever we want to apply this quantum gate to some qubit A, we just multiply n by the state of A. In notation, this would be written like this. So n multiplied by the state of A will give us the state of A prime. Excellent. And we can kind of think about this as we said before, we multiply our matrix. We multiply our matrix by this so we multiply our vector by this matrix n, and we get our result. And we can see here, as we multiply this vector by this matrix n, we will understand that this flips. We multiply A down, A becomes down to here, and B down, B comes to here. Perfect. Excellent. So yeah, that's gates. That's a very simple binary gate. There are some other ones. We're going to mainly just look at NOT gates. We'll talk about some other ones when we give an implementation later. But the idea is that you could represent some gate as some vector that operates on the state, some matrix that operates on our state vector to give our new state vector. Perfect. Now let's think about what would happen if we take another operation, so another quantum gate. This one is also a NOT gate, denoted by the symbol. And our NOT gate is now, so we now have a NOT gate and then another NOT gate. Well, what does our intuition tell us this will be? We've gone from AB to BA. If we think about it again, we should intuitively we should go back from BA to AB. And now let's think about it as kind of more notationally. We've multiplied n by A to get this state here. So I'm gonna call this A star, or with a little asterisk. There's no necessary convention in how you do this. You might want to call this A0, A1, and A2. I've just called this A star and A prime. Doesn't really matter. So the idea here is that this will give us A prime, and then we multiply A prime by n to get, this will give us A star, so A star, and then we multiply A star by n to get us A prime. So we can kind of collect terms, and we can get back to the idea that we'd understand that, all right, we multiply by this gate, and then we multiply by this gate again. So we would write our notation as n, n, a. And it's very important that we make sure we keep our order. So remember that this n is representing this NOT gate, and this n is representing this NOT gate. It doesn't matter because these two gates are the same for the moment, but when we introduce gates that aren't the same, it's very important that we keep the order, because as you well know, matrices are not commutable, and so changing the order will not always give us the right answer. Perfect. So nn. Let's work out what n multiplied by n is. So nn is going to be equal to this multiplied by itself. And doing this will quite clearly give us the identity matrix. Which implies that our state hasn't changed. So two NOT gates will therefore cancel each other out, and our state A prime will be equal to A. Excellent. So we've covered what a NOT gate is. We've covered how we can represent our gates as matrices, and we've discovered what happens when we put our gates in series like this. Excellent. Next thing we're going to look at is what happens when we do operations in parallel. So let me just delete this here so we have some space. All right, so let's draw our diagram again. We have our state, our qubit A, the state of qubit A. We represent qubit A along this line. Remember, this is the direction of time in this way. And we're going to actually introduce a second qubit, a qubit B. So this is the state of B. The state of B going along here. And now let's think about what would happen if we did an operation on A. So this is our circuit diagram here. Now, quite clearly, we could perform an operation on A. So we could perform this operation, this vector, this matrix N, because we know this is a NOT gate, so we know that we will be the matrix N. So we can multiply the matrix N by A to get A prime. And we can multiply the B vector by the identity matrix, because this is just a wire. And nothing's kind of happening, to get B prime. And we can do that separately, and that's nice and fine. But what I also want us to think about is how can we combine these two to think about the system not just as two separate qubits, but rather as a system of two qubits. And so what I'm going to do here is I'm going to introduce this term psi, and psi is going to represent the combined state of the two qubits, which might seem a little odd initially, but don't worry, I'll explain it. So psi prime, so we have psi here representing the combined state of A and B, and psi prime being the combined state of A prime and B prime. And so what does psi prime look like? We know that we can write the state of A in this form, and we know we can write the state of B in this form. What can we write the state of psi as? Well, with psi, what we can say is what are the possible states of psi? If we measure these qubits, which I know I haven't talked about that much, but we will. But the idea is that when I'm talking about these probability vectors, that's kind of when we measure our qubits, they collapse their state and they become definite, which is complicated, and it's how there's a lot of theories behind it, Copenhagen theory and that sort of stuff. Again, beyond the scope of the video, the idea is that they have a probability of being in each state. So let's think about the possible states we can have our qubits A and B in. So the initial one, obviously we can have A is 0 and B is 0. What other ones can we have? Well, we can have A is 0 and B is 1. We can have, I'm going to write a C. That's a very bad C. You should understand that's a C. A is 1, B is 0. And we can have A is 1 and B is 1. So we have 4 states. And if we remember how we did this, we're going to imagine these states as unit vectors, and these coefficients of unit vectors as well, they're coefficients of unit vectors. And the combined, as we sum up these coefficients multiplied by the unit vectors, we end up with our vector of states, which gives us kind of the information about the superposition of both A and B as a system. And this is quite an important idea and a really useful concept to learn. And we'll talk about why this is so important later when we talk about 2-qubit quantum gates rather than just our singular 1-qubit quantum gates. So again, we can write this as a column vector, A, B, C, and D. And we can do matrix multiplication with it. Now, what's a bit interesting here is that, all right, we want to get from, so we know that we can represent this operation or these collections of operations if we're thinking about the identity matrix as an operation, which is useful to do. We can think about these operations, these collections of operations, as one singular matrix that transforms psi into psi prime. And how would we think about it? I mean, what would we need? Well, we've got a 4x4 matrix. We've got a 4x1 vector. So to get it to be a 4x1 vector, we need a 4x4 matrix to transform it. Unfortunately, this NOT gate only gives us a 2x2. And this identity is also, this identity matrix, I'm going to write the matrices above. So this NOT gate is only a 2x2. And this identity matrix is only a 2x2. How do we get from a 2x2 to a 4x4? Well, that's where a useful product comes in. And I guess, well, I would have guessed. I mean, I never came across it. So I would be surprised if you have come across it. But correct me if I'm wrong in the comments. I'm just going to put this up here for the sake of kind of keeping this in our mind, but out of the way. I'll move this down. Logistics of Microsoft Paint. Wonderful. Put this up there. All right, excellent. And we've cut off the tip of our N. That's not ideal. We'll just fill that one back in. Yes. So what I was talking about, we were talking about, all right, we want to get from this 2x2, these two 2x2s, to a 4x4. And we use this thing called the tensor product. So we have N, tensor product, I. Excuse my phone. So we have N tensor product I. And the idea of a tensor product, if we remember what N is. So remember what N is. N is going to be equal to this vector 0, 1, 1, 0. And our identity vector, our identity matrix, is going to be 1, 0, 0, 1. So N tensor product I, remember we're going to write it as a 4x4 matrix. And the way we take this is we take our N and we spread it out. And in each of these 4 spaces, we multiply it by the entirety of the vector I, of the matrix I. So we would do this like this. 0 times 1, 0, 0, 1. 1 times 1, 0, 0, 1. 1 times 1, 0, 0, 1. And 0 times 1, 0, 0, 1. Excellent. Expanding this out, I will erase it. You can have a go expanding it out. It's not particularly difficult. I will do it for you here. I'm just going to write it out. And remember what this vector represents. This matrix represents effectively the transform on the entirety of the 2-qubit state. 2 qubits, A and B. Their state itself is described by psi, and we're taking the whole state and multiplying the entirety of the state by this vector. Sorry, this matrix. Getting vector and matrix confused a lot. Quite funny. All right, let's think of a simple example to give us an intuition of how this works. So let's think of if we have a state 0, 0. So both A and B are definitely off. So in a state 0, 0, A is going to be 1, B, C, and D are all going to be 0. So we're going to have 1, 0, 0, 0. And what's useful about this configuration is that since we only have a unit vector here, we can just look at this column and that'll give us directly the output. So in this case, I'm actually going to, well, I'll write it out. In this case, our vector is going to go from 1, 0, 0, 0 to 0, 0, 1, 0. And so what's that done? If we look at this, this is going to be coefficient C. C implies 1, 0, the state 1, 0. Does this comply with our intuition? Well, B is going to be 0 and A is going to be 0. B is going to stay the same, so B is going to be 0, which is correct. And A is going to be knotted, or flipped. So A is now going to be from a state of definitely 0 to a state of definitely 1. Excellent. So this complies with our intuition. We've gone from a state of 0, 0 to a state of 1, 0. And this is useful. Of course, here we're just looking purely at what happens with a definite state. But the important thing to keep in mind is that the usefulness of a quantum circuit is that you can do this with superpositions of states, and it can, it'll still work. The idea is still kind of following. All right, perfect. So we looked at series calculations. We've looked at parallelization. We've looked at so qubits in series, qubits in parallel. We've looked at quantum gates in series, quantum gates in parallel. Excuse me. And we've looked at the idea of a quantum gate itself. Perfect. All right. The next thing we're going to look at is we're going to look at what happens when we have a 2-qubit quantum gate. Let me just erase some of this information here. And if we connect this, so our 2-qubit quantum gate looks like this. Ignore the slightly wiggly line. All right, and so the idea behind this gate is going to be called a CNOT gate. And that stands for controlled NOT gate. So we have our NOT gate here, and what effectively we mean by when we say controlled is that this NOT gate is controlled by this other qubit. So this NOT gate only works, it only turns on, you could say, when this other qubit is on. So let's imagine B is off and A is off, right? B is off, so therefore this NOT gate, this controlled NOT gate is not activated. Or this NOT gate here is not activated. So therefore A stays off instead of being flipped to a 1. Now say B is on and A is off. Now when it passes through, because B is on, A is flipped to the on state. Because it was in the off state, it's now flipped to the on state. Now let's have a think about what we'd expect this to be as a matrix. So remember, because it's a 2-qubit quantum gate, we have 2 states, and so therefore to describe 2 states we need 4 rows. So in the first row we have, so let's think about it logically. The first row represents the state if we have off, off, right? And as we discussed, off, off, this doesn't activate, So therefore this NOT gate is not on, and this stays off. So it'll be in the off state still. Now, what happens when we have off on? Sorry, on off. Yeah, on off. And because B is still off again, our on state is not going to be flipped. So our on off will be transformed to on off. So it'd be transformed to itself. Now let's think about off on. And because this is activated, this will flip. So therefore our off on becomes on. So our transformation will not be the same and look like this. And our final state, on, this will be flipped because this is activated. So this NOT gate is activated. And so we end up with the state, with the row that looks like this. Perfect. So we now have our matrix for our controlled NOT gate. And this is a useful idea, and the kind of what becomes useful is because we've represented it as a 4x4 matrix, we're looking at the state of the system as a whole. So we can then add extra gates onto the end. Yeah. And then think about, instead of just this, we think about what the combination of these gates are. So this is a NOT gate, and this is an identity gate. We're going to write this as a CNOT gate. So CN, representing CNOT gate. And this represents the entirety of both qubits. So we're going to multiply. So if we want to see what happens to the state as a whole through this entire transformation, we're going to look at this. So we do this multiplied by our state, psi, multiplied by n tensor product I, because remember we're looking at the system as the state of the system as a whole, not one singular qubit. And because we have this controlled NOT gate, there's a 2-qubit NOT gate, it's very important that we keep looking at it as a 2-qubit system, because we can't now compute 1 qubit at a time because they're connected. So 1 qubit relies on the other qubit. Excellent. So the way we'd write this, we'd have our CNOT gate, and we'd have our NOT gate tensor product, our identity matrix. Now, I am not going to expand this all out because it'll take quite a while and it's kind of beyond the scope of the video. But I will leave this as a good exercise for any of those that are interested. It's quite interesting to see what comes out and to test your intuitions. Perfect. Again, to note with the C controlled NOT gate, as to note with any gate, we've only looked at definite conditions. This matrix stays the same for indefinite conditions, but you can imagine what would happen if we put in some different values of A, B, C, and D. And you can play with that and look at conditions where the state of the system is not definite. Perfect. All right, the final thing we're going to move on to is we're going to move on to an implementation of all this knowledge we've put together. Our goal now is to entangle 2 qubits. Now, what do I mean by entangling 2 qubits? I mean, we want to... We want to make it so that if we measure 1 qubit, the state of the other qubit will be definite. Will become definite. So we start with a state that's indefinite, and when we measure 1 qubit, measuring that qubit, the act of measuring that qubit defines what the other qubit has to be. Let's look at a state where this is. Let's look at the example state. So this state here is called the Bell state, named after someone Bell. Excuse me, I will put that in the description. I should know his name. Whoops. And the Bell state is written like this. I stood up already. 1 over root 2. It's a 2-qubit system. And we're looking at the entire system. 1 over root 2, state 0, 0, plus 1 over root 2, state 1, 1. Now, why is this entangled? Why might you say is this entangled? And the reason for what makes this entangled as a state is that, say we measure a qubit. So remember that psi represents qubit A, qubit B. So this one's going to be, so so we're in this state, right? If we measure one qubit, say we measure the first qubit, and we see that the first qubit is 0, in the state 0, all right? Now we know that because this qubit is in state 0, the other qubit can either be in state 0 or actually nothing. It can only be in state 0. Like, there's no state. If we were to extend this, we have 0 multiplied by the state 0, 1. So there's a 0% probability that our 2 qubits are in the state 0, 1. So if we measure the first qubit as 0, we know for sure that the second qubit is 0, which is pretty crazy. And kind of, you can think of the ideas of this. I mean, in a quantum computer, it seems less impressive because both qubits tend to be very close to each other. But in actuality, in quantum mechanics, people can entangle qubits using the method I'm about to show you, and then separate them. And then when you measure one qubit, the second one collapses its state into a definite state instantaneously, or apparently instantaneously across as so far as we know, which is very interesting. So, without further ado, let's look at how we get into this state. First, before we get into this problem, we need to look at one more quantum gate that's going to be very useful for us. And this gate is called the Hadamard gate. So we go back to our 1 qubit. We look at qubit A. And we pass it through this Hadamard gate, gate H, to get A prime. Hadamard gate. What does the Hadamard gate do? Well, this is the matrix for the Hadamard gate. That's a horrible bracket. Or 1 over root 2, 1, 1, 1, negative 1. And let's think about what this Hadamard gate will do. So let's plug in the values. Let's say A starts as a definite 0. All right? So we plug in the values 1, 0. Remember where we get this from. A being 1, so it's in a definite state of 0, and B being related to the state of 1, which is obviously B is 0 because there's a 0% probability as well. All right, excellent. We multiply these together, and what does this get us? Well, this gets us 1 over root 2 and 1 over root 2. So A is going to be equal to 1 over root 2, and B is going to be equal to 1 over root 2. Great. So what this gate here does is it puts A from a definite state into a superposition of states. So we've gone from a definite state of 1, 0 to a superposition of states of half. Remember, we have to square these. Half of it. So the probability of it being 0 is 1, and the probability of it being 0 is a half, and the probability of it being 1 is going to be a half also. So it's not only a superposition of states, but it's an equal superposition of states. Perfect. All right. Enough about the Hadamard gate. Let's move on to our final implementation on how we are going to create an entangled set of qubits. So, what we're going to do, we have our 2 qubits, A and B. And they have their final state, A prime and B prime. And we have the state of our entire system, psi, and the final state of our entire system, psi prime. And for this example, to entangle our qubits, we're going to set A and B equal to 0. So our qubits start off in a definite state of 0, 0. Perfect. So how are we going to do this? Well, if we look at our target, we also remember that our target, this is the state we're trying to get. 1 over root 2, state of 0, 0, plus 1 over root 2, state of 1, 1. So let's think about how we're going to do this. We see that there's an equal superposition of states. So it makes sense that we have to have a Hadamard gate in there somewhere. We start with a definite set. If we start with a definite state, all of the other gates we've looked at so far, the NOT gate, the controlled NOT gate, and just the identity matrix, which is just doing nothing, they're all go from definite state to a definite state. So we need something that goes to a indefinite state or an equal superposition of states. All right. So let's put a Hadamard gate in on A. So we're gonna put a Hadamard gate here. Ooh, we use a fancy box. Very cool. And we put a H. So we have a Hadamard gate here. So remember, because we don't have a second, we don't have any 2 qubit quantum gates in this diagram so far. We can think of this as operating as operating in parallel. So B is still going to be 0, and A is going to now be in a superposition of states. All right. So I'm going to write this as A star, so we can keep track of what's going on. So A star is in the superposition of states. So at the moment, A star looks like this. 1 over root 2. My 2's. 1 over root 2 state 0 plus 1 over root 2 state 1. Perfect. So we've gone from a state of 0 to a state of an equal superposition of states of 0 and 1. Nice. Now what we want to do is we want to say, all right, if A star is all right, we want to say if A happens to be 1, we want to flip B so that it goes from 0 to 1. And if A happens to be 0, we want to keep B as it is. Now, remember, we're still thinking in kind of in definite terms, but actually, this approach still works for an indefinite term. So even though we've got an indefinite state, we can still think as though it's a definite state. And so what we do is we put our controlled NOT gate in here. What? Excuse me. So we put our controlled NOT gate in here, and we're now, what we're doing is we're saying, oh, actually I've got it the wrong way around. Excuse me. Put our controlled NOT gate in here, and what we're saying is that when A is 1, we want to flip B, and when A is 0, we want to keep B. And so instead of looking at just the state of A, let's look at the state of psi star here. And what's the state of psi star? Well, the state of psi star is going to be, as a tongue twister. the state of psi star is going to be very similar to the state of A star, but we're just going to add a little extra term, 0, to the end of this, because this, the state of B is going to be always 0. All right, so we've got this state. Now let's shrink this up so we can do some computation on it. Let's check if our intuition is correct. We have not been lied to by our intuition. So this is our state. Oh, let me replace A with a psi. So we've got it correct. All right, so remember how we'd write this. Psi star, if we put this in the column vector, all right, we look at our table. A is going to be a 1 over root 2. B is going to be 0, because there's no state with B as 1 so far. C is going to be 1 over root 2, and D is also going to be 0. So we've got our matrix, sorry, our column vector. 1 over root 2, 0. 1 over root 2, 0. Excuse that very strange 0. And we're going to multiply it by a C0 gate. Zero, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. And if we multiply down, so we're going to have a half multiplied by this column. So it's going to be a half in this box here. And we're going to have a half plus a half multiplied by this column. So a half in this box here. So our final state is going to be 1 over root 2, 0, 0, 1 over root 2. Perfect. And let's convert this as a final task back into our state. So this is going to be state, remember we're multiplying, we've got the state of psi star here. We're going to multiply it by the C0 gate, which we've just done, to get the state of psi prime. So the state of psi prime is going to be equal to 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. And this is our entangled state. This is the Bell state. This is exactly what we wanted. Perfect. Mission accomplished. You've just managed to create a circuit diagram, or we've just managed to create a circuit diagram for a process which entangles 2 qubits. Congratulations. All right. Thank you very much for watching this video. I know it's a bit kind of it's a little bit janky with the Microsoft Paint. My drawing is not very good, but thanks for watching anyway, and very well done if you managed to keep it to the end. I know I can be interesting to listen to it sometimes, but yeah, no, it was great to Thank you very much. Please consider subscribing. I'm thinking about putting out some more videos on other topics, just things I'm interested in. And yeah, excellent. Let me know what you think.